see. All right, awesome. So, hi everyone, I'm Veronica Shoenfeld, a senior mathematics major in the pure concentration, and today I'm presenting the second section of my senior honors project, limiting processes, the speed of convergence of iteration sequences. So today I am presenting the problems from the following paper, Applications of the Squeeze Theorem to Limiting Processes Involving Riemann Integration by Brian Bissey, Solomon Huang, Bogdan Suchava, and Ashley Tunaguayo, and myself. The paper was accepted for publication to the College Math Journal and should appear soon in the Classroom Capsules section. Let's see. All right, so students are first exposed to the squeeze theorem in their first year of differential calculus. So here at Cal State Fullerton, that would be Math 150A. But in this course, students only experience the most elementary applications of the squeeze theorem, mainly involving limits of trig functions. But today we are going to look at more advanced problems that can be solved with the squeeze theorem. Oops. All right, so recall the squeeze theorem. So if we have three functions, f, g, and h, suppose g is bounded between f and h, and if we take the limit of f and h and they're equal, we'll say equal to L, then the limit of g would also equal L. So yeah. So before we move on to the more advanced problems, we're going to just look at a very simple problem using the squeeze theorem. So this is from our Stewart calculus book that we use here at Cal State Fullerton. So we want to evaluate the limit as x approaches 0 of x squared times cosine of 1 over x. So first, we know that the function cosine is bounded between -1 and 1. And when x is not equal to 0, we can also say cosine of 1 over x is bounded between -1 and 1. And so now we want this, this portion right here to look like our original limit. So we're just going to simply multiply everything by x squared. And when we take the limit of everything in this inequality, then we get the limit is equal to 0, simply because the limit of negative x squared and x squared is equal to 0. So it squeezes our original limit to 0 as well. And here is a visual of that. So here in blue is that x squared times cosine of 1 over x, that's that function. And then in the red is our positive x squared and negative x squared function. So you can see as we get closer and closer to 0, the two red functions squeeze the blue one to go to 0 as well. So let's see. All right. So for our first problem that we look at, it's from the Gazzetta Mathematica from 2017. And here we want to find the limit of this Riemann integral. So we're going to use the squeeze theorem to solve this because solving it directly would be very difficult. So looking at the interval A, we see that tangent and cotangent are strictly positive. And from the interval of our integral, tangent times cotangent is 1. So from here, we know we can use the AM-GM inequality, which is the arithmetic mean and geometric mean inequality. And from here, we get tangent to the nth power plus cotangent to the nth power is greater than or equal to 2. And comparing that to our denominator in the integrand, we get this inequality now. So we can compare our original integrand to this √3 over 2 to the n. And like we said earlier, we are working with strictly positive values. So we also know that's greater than 0. So now just taking the limit of our right-hand side, we get 0. And by the squeeze theorem, our original problem is just 0. And that's a lot simpler than doing this directly. All right, so now for our second problem, it's also from the Gazzetta Mathematica from 2019. So again, we want to find the limit of this Riemann integral. And again, we'll use the squeeze theorem. So here we can estimate, we could estimate our integral with this one right on the right-hand side because arctangent is bounded above by pi over 2. So that's how we get this. And now we can take this denominator right here and multiply everything by n. And we can estimate it even further to say it's larger than this value right here. And so now estimating our integral even further, now we have this on our right-hand side. And it still looks a little complicated, but if we take that right here, we could just factor out this n minus 1 from our integral, and now we have like this very simple integral from Calc 2, which is just arctangent. And evaluating that, now we have this new right-hand side. And estimating like we did earlier, we can say this value is now less than pi squared over 4 times n minus 1. And now taking the limit of this, it's always going to be 0 as n approaches infinity. So now we can say our whole integral, the limit approaches 0 as well by the squeeze theorem. Let's see. So, sorry, there's a couple things in the chat. Okay, awesome. So it is 11:19, so I'm just gonna quickly go over my third example here. So this is from 2017, and again, we want to compute the limit for this. So to start, we're gonna take this, our integral, and subtract this integral from 0 to 1 of natural log of x plus 2. And working with this, we end up all the way here to this estimate right here. And now taking that limit, we have it goes to 0. And going back to our original problem, this is what we started with. Now we know all of this is equal to 0, and then moving this integral to the other side, we have this equation right here, and solving this integral on the right-hand side is very simple. And we end up with 3 natural log of 3 minus 2 natural log of 2 minus 1. So those are just a few examples on how we can use the squeeze theorem to solve these limiting processes of Riemann integrals. In the rest of my thesis, we'll use these techniques to investigate the connection between the Stolz-Chazaro lemma and the behavior of discrete dynamical systems, which hopefully you'll all be able to read after the semester. And let's see, here are my references. And I would just like to say thank you to everyone that is here today, especially Dr. Suchava, who has helped me a lot in the last year with this project.